this, so please give her the credit. I am just the messenger. That's a bad sign. At this point, I would be motivating automatic parallelization and telling you how we're living in the multi-core era nowadays. And nowadays, if you want good performance, you need to somehow extract thread-level parallelism from your applications. At this point in time, we have algorithms that can do this in many cases. And there have been a lot of great successes at getting scalable parallelism. However, there still are some lost opportunities. I'm going to walk you through them. So, I see. I don't know how to use Mac. Thank you. Sorry about that, guys. I don't know how to use Macintosh. So yeah, this talks about automatic parallelization. And there have been some successes in automatic parallelization, but there's still some work to be done. So let me give you a more concrete example. Consider this function. It's a hot function, by which I mean it's using a lot of the time of the program's total execution, and it consists of a loop with independent work. As it executes sequentially, we can represent the way it looks this way, where the horizontal axis is parallel resources such as cores or processors, and the vertical axis is time. I'm drawing as each rectangle one iteration of the loop. Before the multi-core era, we would hope that microarchitectural improvements would make these shorter and shorter as to decrease the total execution time of this loop. But with automatic parallelization, algorithms can transform this code so that iterations of this loop can be distributed across cores and greatly decrease the total running time of the loop. This is great, but there's a missed opportunity. However, in a real application, your application is more than just one hot loop. It's very unlikely you can parallelize the entire application. And it's likely, however, that your loop will be within a greater application and your parallel region will be invoked multiple times. So for example, here I have a loop which will invoke my hot function. And this is fine because when I execute it, during the second iteration of this loop, we see another parallel invocation and again, a lot of savings in time through parallelism. However, at the same time, I want to point out there's a lot of wasted time in here. There are a lot of times where the cores are not doing any sort of work whatsoever. And all of this wasted time I'm calling the barrier penalty. The problem is that when we parallelized the inner loop, we inserted a barrier at the end of the parallel region to ensure that every worker had completed their work. This is necessary for correctness, but I will show you that it's actually somewhat overly conservative, and we can probably do better. Now, that's not to say that it's completely unnecessary. There could, problem with the barrier penalty is that each parallel invocation is going to take time governed by the longest running worker within that stage. If some work units actually execute much more quickly, then we have this wasted work. But this is not to say that the barrier is completely unnecessary. You could imagine, for example, there is a data dependence from some work in the first invocation to work in the later invocation. It's very important that a compiler respect this data dependence in terms of the ordering and time at which iterations can execute, otherwise it might change program behavior. So we need something more fine-grained than a barrier, but more restrictive than free-for-all. So what is a better execution model? Well, let me show you. Imagine that we could move iterations from the second invocation up sometimes. In cases where synchronization still is necessary, there's an obligatory pause, but other iterations can be moved earlier. As a consequence of this, we'll see there is still some wasted time near the end, but at the same time, we are seeing an overlap between these two invocations. And at the end, we're getting a savings in time at the end. This is a savings in time which is going to add up again and again and again with every iteration of the outer loop. So I'm going to try and show you how we achieve this. But at a high level, let me explain what we're trying to achieve more specifically. First of all, we want a solution to this problem to be fast. And I'm highlighting the overlap between these two invocations. Exploit that additional time where we're otherwise wasting resources. We want this system to be safe. If there are cross-iteration dependencies, we want to be able to realize that in terms of a stall and prevent data races between these two invocations. We want this system to be robust, which is to say that compilers are, by and large, stupid, and if our static analysis is not smart enough to tell us all of our answers, we still want to be able to take advantage of this opportunity. We want this to be a graceful system, so if we're not going to pay a penalty for any sort of misspeculation or rare occurrences. And finally, we would like this to be an automatic system. So, the way I've described the problem, a couple things might pop into your mind, and let's go over a few of them. First question is, why not just parallelize the outer loop? And I agree, if you can do this, this is the best way to do it. The problem is you're not always going to be able to do this, and if you consider larger and larger loops from higher and higher in the loop nest, your chances of being able to parallelize it are going to decrease because it will include more things such as I/O and side effect and operations. So we have to mark that off. Another possibility seems to be work stealing. Unfortunately, work stealing is not necessarily a solution. The reason being that during the process of work stealing, you might end up reordering some iterations unless you take special effort to prevent that. And it doesn't answer the question of how you determine when that situation might arise. So for example, if these two columns represent work queues for two different workers, you can imagine a case where the second worker is retiring work units a lot faster than the first worker. The second worker steals a work item, but in doing so reorders iteration C to happen after iteration B. And as a consequence, this could cause a data race. Another solution would be speculation. Speculation comes very close to solving this problem. When I say speculation, I'm speaking very broadly about techniques such as transactional memory, software transactional memories, speculative lock elision. The problem, there are a couple problems with speculation. First, if you're using a software transactional memory system, then there are going to be a cost for the speculative validation that you have to pay in the common case. And it's wasteful, we would like to avoid it. Another problem with speculation is the possibility of misspeculation. Misspeculation can be tolerated if it is very rare, but nothing about the way I've described the problem so far should make you think that it's necessarily going to be rare or probabilistic. In fact, for these problems, it could be that a misspeculation occurs regularly, say 50% of the time, every other iteration. So speculation is just not going to work for this problem either. Our approach is a little different. We're starting off, we're going to actually dedicate one thread to the problem of identifying when workers would need to go and when they would need to wait for synchronization. We compute this at runtime using runtime information as a means to avoid the problems of static analysis. The scheduler is going to compute this information and then send instructions to the worker processes telling them either to proceed and do work or to pause and wait until the necessary preconditions have taken place and then begin work. There's no communication between the workers. The workers do not talk to one another. They're going to publish through shared memory their progress through their work units, and this allows the workers to coordinate without stalling on one another. So let me draw a picture to make this a little bit more clear. Again, we're looking at a timing diagram. Cores are horizontal, time is vertical. Unlike before, we're adding in these yellow rectangles which represent work done by the scheduler thread. The scheduler can then issue commands to the other worker callers, causing work to begin on those cores. and it can do it again, and it can do it again. Now in this case, I've highlighted one of these rectangles in blue. It says wait. I hope you can see it in the back of the room. In this case, the scheduler has identified that there is some sort of a runtime dependence which will cause that work unit to need to wait before it can proceed. But then, via the publishing mechanism, this dotted line, we see that another iteration has finished, and then that worker can begin. This is pretty close to our original ideal execution model, with one big difference. There's a big pipeline fill. In fact, this thing very much resembles a pipeline. While it is still filling up, some cores are idle. However, the instructions sent from the scheduler to each one of the workers are queued up in a communication queue. And since the scheduler runs faster than the workers, it will eventually reach a steady state in which the queues are full, and the workers are not going to stall waiting for the scheduler. They're only going to stall if need to be for the dependencies, to respect dependencies. So at this point, I need to convince you of two more things. I need to convince you that one can construct a scheduler, and I will need to convince you that the scheduler can determine these dependencies at runtime. So at a high level, our scheduler design is going to resemble the inspector executor system, which was published in the 90s. Under this system, we're going to use the scheduler to simulate execution of the original application, but we will do so without any sort of side effects. So it's safe to do this ahead of time, and we can use this to collect information to determine dependencies. To make that efficient, we will use a shadow memory scheme and record metadata at the per byte granularity in shadow memory. For those of you familiar with profiling, this will very much resemble memory profiling. And finally, the scheduler, as I said before, will communicate to the workers, but the workers will never communicate back to the pipeline. This creates an execution model where we can get a full pipeline. And this is very similar to, say, a pipeline processor. So, to compute the scheduler, we will do several things. Ideally, the scheduler needs to have the address of every memory access performed within the parallel region. So to do that, we compute a reverse slice of all of the pointers used by the parallel region. For example, if this were our original code, it's just a loop which chases a linked list and does work on it, and the corresponding program dependence graph to its right, we would first identify a pointer, which will be dereferenced via load, and then we will transitively find all of the operations which contribute to that. This gives us a partition of the code into two halves, an orange half and a white half. Next, we're going to figure out a way to divide this into two different pieces of code, the scheduler code and the worker code. The way we do this is based upon the MTCG, multi-threaded code generation algorithm, Tony et al. The details are kind of complicated. I'm going to wave my hands a little bit and just show you pretty animations, but the details are in the paper. We first put all the orange instructions in one thread and the white in another. We replicate some control flow in order to make the program sane, and we insert some inter-core communication via produce and consume so that no redundancy is done between these two. No redundant computation is necessary between these two workers. Next, let me tell you how dependence detection is happening at runtime. So if this were our original program, the scheduler thread will be divided in the way I showed you before, but with a few other changes. First, we need to add a callback, which will report the iteration to a runtime library. This gives us a notion of the boundary between work units. Second, every time that the original program would perform a memory access, a load or a store, we replace that load or store with a callback into our runtime library to report the address of that pointer. Then at runtime, we use two auxiliary data structures. We use a shadow memory array, and we use a set of inter-process communication queues from the scheduler to each of the workers. These are first in, first out queues. And to demonstrate the algorithm, I'll just walk you through a few iterations. We start off, we report the iteration, and the runtime library knows what iteration we're in. And then at each memory access, the runtime library will take the dynamic value of that pointer, find the corresponding metadata in shadow memory, and record that this worker will touch that memory. Continues a little bit more, continues a little bit more. And by the time we reach the end of the iteration, the scheduler is able to send a go command to one of the workers, indicating that this iteration is free to execute, no synchronization is necessary, and there will be no data races. And then let's look at another iteration. At this point, our concern is, if we start another work unit, will it be independent from the one that is currently being executed? So again, the iteration count is bumped. We observe more stores. And thankfully, in this case, we see that each one of the memory accesses was disjoint from what was done by the previous iteration. Again, where the scheduler is able to tell the worker to begin. What about a more interesting case? In this case, during the third iteration, which I numbered T2, pointer refers to a memory address which was accessed during the first iteration. So if both of these two worker processes access the same memory, there's an opportunity for a data race, and we want to ensure there is some synchronization. When the runtime library observes that both T1 and T0 will touch this iteration, this memory address, it will send a synchronization token, a wait token to that worker. It continues through the next of the iteration until it reaches the end of the iteration, and then sends a go command. So to be clear, these are ordered. Worker 2 is instructed to wait for worker T0 to finish iteration 0, and then after that wait, it can begin with iteration 2. And then one more time, we see a similar pattern. We look up pointer addresses, record stuff in shadow memory, and when we see a conflict, like here, we tell it to wait, and then tell it to go after it's done waiting. So this seems like a lot of stuff. Does it really solve the problem? How much does it help? To evaluate this, we found some benchmarks from various benchmark suites where we could parallelize an inner loop, but we were unable to parallelize the outer loop. As a result, these benchmarks, which I hope you can read from the back, suffered a barrier penalty again and again and again. After transforming it through our system, we were able to greatly increase the scalability of some of these benchmarks. For example, CG in the upper left-hand corner turned in from a slowdown benchmark into a speed-up benchmark. Black-Scholes was able to scale a lot further than it was without our technique. LLU bench similarly was able to scale much farther. It's not a solve-all. There's some benchmarks like mgrid where we turned a really bad parallelization into a less bad parallelization, but hey, nothing's perfect. So to conclude, I just want to say that there is a lot of inter-invocation parallelism available, and the barrier penalty can be significant, and that we can do better than that automatically. Thank you very much.
Questions?
Hi, nice work. It seems like there's sort of, in order for this to work well, you had your orange instructions and your white instructions, and you need those orange instructions to be a pretty small fraction of the work that you're doing in a given task, right? Because that's the sequentialized part of the computation. Can you comment on how easy it is to tell how effective it's going to be to try to use this kind of model?
Yeah, I see what you're saying. I was confused at first because I thought they were yellow, not white, but no problem. Yeah, in general, this will work if the balance between the scheduler thread and the actual work units is significantly weighted towards the work units. So we hope the scheduler should be cheap. and for some benchmarks it is. One could try to estimate this statically. There is reason to believe that it will always be a little bit smaller since we compute the scheduler by removing instructions from the worker. But I cannot really make guarantees in generality. Thank you.
Hi, I am from the Institute of Computing Technology, Chinese Academy of Sciences. I have a question that I think that what you have done can be done by the task-driven parallelism, and which are supported by many compilers. I mean the task-driven.
Task-driven parallelism?
Yeah. Can do the same thing.
Well, I'm not familiar with precisely the technique you're referring to. In the paper, we do give details about how this technique can be composed with other parallelization techniques. The slides made it look simpler, but in the paper, we show how it composes with dual, obviously, as well as the local right parallelization and a third one, which I forget right now, of course.
And I know many compilers like the Silk extension of ICC can do this work. So your work is performance better than that. I mean, have you compared the performance of the applications written by your method to the auto parallelization done by the ICC?
Unfortunately, no, we have not done that comparison. This comparison here, the two curves are our compiler in green before the technique and our compiler in red with the technique. So we do try and compare this to parallelization without this sort of technique. But in terms of comparing to industry-grade parallelizing compiler, we have not done that. And hopefully we'll do that in the future.
So I have one more question. So you mentioned that this is similar to the Salts et al. Inspector Executor. Is there different code in the inspector, or is it just the fact that the scheduler does the signaling so that you can bump everything up together a little better?
Okay, so I think there were two things there. First, you were asking to differentiate from Inspector Executor.
Right.
Okay, so.
And then I speculated as to what your answer might be.
Yes. So Inspector Executor is actually done in 3 phases. There's an inspection phase where you sequentially execute the entire parallel loop to determine dependencies. Then you have a scheduling phase, and then only after the scheduling phase do you identify, well, during the scheduling phase, you identify wavefronts which you execute in parallel. One major difference here is that we're executing our scheduler and our workers concurrently. We do not have to wait for inspection and scheduling to finish before we can begin. Another difference between IE and this work is that IE is, by using wavefronts, it has more freedom to distribute the work across cores. We're choosing a fixed round-robin distribution strategy, and that makes the scheduler simpler at runtime. And did I get your second
Yes,
question?
yes, you answered me well. Thank you very much. Thank our speaker one more time. Chen Gang is going to give us some insights about how to